this video series on stacks and queues. In this first part, we'll give an introduction to stacks, as well as design and implement a basic stack in Java. We will assume basic familiarity with list-based data structures, so if you've not already watched those videos, you may want to start there. The collection data structures that we've seen so far, such as lists and sets, are unstructured in that they simply hold elements. Lists may hold elements in a certain order, thus there's the concept of the first element, the second element, and the last element, etc. However, there's no further structure beyond this that could potentially be exploited for efficient operations. Applying a sorting algorithm to a list can impose a structure on the list, but only temporarily, as adding elements or otherwise modifying the list may ruin that sorting. Thus, it's easy to see that order is not the same thing as sorting. These notions of structure, that is, order and sorting, are aspects of a data structure's state. Alternatively, some data structures impose order through a collection's behavior, which is defined by the data structure's publicly available interface. We'll look at several of these types of data structures that achieve this by restricting which elements can be accessed and in which order. Our first restricted access data structure is a stack. A stack is a data structure that stores elements in a last in, first out, or LIFO manner. This is realized through two core operations, push and pop. A push operation adds an element to the stack at the top of the stack, and a pop operation removes the element at the top of the stack. Thus, the last element to be pushed is the first one that gets popped. A stack is best visualized, as the name implies, as a stack of elements piled one on top of the other. We can add elements by pushing them onto the stack. Each one is added on top of the other via a push operation. Like a stack of dishes, however, we don't want to pull a dish from the bottom or the middle of the stack, lest we risk the stack falling. Instead, our access is restricted to the top of the stack. As we remove elements using a pop operation, the order in which they come off is the reverse of the order that we push them. When designing a stack, there are several considerations that must be made. First, a stack can be bounded in size or allowed to be unbounded. A bounded stack has a fixed capacity and can only hold a certain number of elements before it's considered full. An unbounded stack can grow with no fixed limit other than the memory of the program or the computer itself. In addition to the two core push and pop operations, there are many secondary pieces of functionality that the stack can support. For example, you could design a stack to provide a way for the user to determine its size. You could provide convenience functions to determine if the stack is empty or, in the case of a bounded stack, whether or not it is full. Another convenience method is a peek operation that allows you to retrieve the topmost element in the stack without actually removing it. We could also provide an index-based retrieval method or an iterator to allow a user to access all the elements of the stack. However, we would not necessarily want to provide a means to modify or remove arbitrary elements in the stack, as it would be counter to the design of the data structure itself. If a user needs the ability to arbitrarily modify a stack, they would do better to use a proper data structure, namely a list. There are also several design decisions that would need to be made. In particular, what does the stack do for edge cases, such as attempting to pop from an empty stack or push an element onto a full stack in the case of bounded stacks? There are several options. We could have the operation fail silently, resulting in a no-op, or no operation for short. In languages that support it, we could throw an exception back to the user to let them handle it. Or we could return a dummy or flag value to indicate the operation had no effect. In the case of pushing onto a full bounded stack, we could return a Boolean false value to indicate that the operation had no effect. In the case of popping from an empty stack, we could return a null reference, as long as we gave the user the ability to distinguish whether or not it was a flag value or if null had actually been pushed onto the stack and validly returned. There's also the main question of how to go about implementing a stack. We'll explore two ways of implementing a stack using a list data structure. Either a linked list or an array-based list can be used, and each option presents its own advantages. I've created a stack class and specified the push and pop methods. Note that it's already been parameterized, so that our stack can hold any type of elements. First, we'll need to define the state. Using composition, we'll have our stack own a list. We'll use the Java Collections library list interface and implementations. Initially, we'll use a linked list implementation. We now need to implement the push and the pop methods in terms of the methods of the underlying list. This involves adding and removing elements from the list, but we need to be consistent about which end of the list we perform these operations on. We could add and remove from the front or the end of the list as long as it's the same for both methods. Let's both add and remove from the front of the list, that is at index 0. Since we're using a linked list, adding and removing from the head is an efficient, constant time operation. Now let's write a few of those secondary methods that we mentioned. A size and isEmpty method are straightforward then. Also easy is a peek method. Instead of removing and returning the element at the head of the linked list, we only have to return it. Let's briefly test our implementation. If correct, this program should output our message successfully. The message is printed in order, because we pushed each element in reverse order. Finally, let's make it so that our stack is optionally bounded. First, I'll create a capacity variable to keep track of the maximum size allowed. Now I'll create a constructor that allows a user to specify this, but also modify the default constructor to use a default value as a flag to indicate that this stack may grow unbounded. Again, it's best practice to have more specific constructors call more general constructors using the this keyword. I'll modify the default constructor to do this. And we don't have any repeated code. Now I'll modify the push and pop operations to take this bound into account. The second exception that I wrote does not really involve the maximum capacity, but makes both methods consistent in their behavior by throwing an exception for corner cases. We would have had an exception popping from an empty stack as before, but it would have been an index out of bounds exception or something similar, exposing the details of our implementation. Let's quickly test this, reusing our test code from before. I'll change the capacity to 3. We should expect an exception at this line when we try to push a fourth element. Let's see what we would need to change if we decided to use an array-based list implementation instead of a linked list. That's it. This really highlights the power of abstraction. We referred to our list as its interface, rather than a specific implementation, so that we could easily swap it out without changing another line of code. There is a problem here, however. We're still pushing and popping from the front of the list. Now that this is an array list, this means that all of the elements will need to be shifted up and down for every operation. Push and pop are no longer efficient constant time operations. They are now linear. We can easily fix this by changing the push, pop, and peek operations to operate on the end of the list instead of the beginning. This code will now work in both cases, whether or not we used a linked list or an array-based list, and will be efficient for either implementation. In summary, linked lists are good for implementing unbounded stacks, as they do not require the resizing of an underlying array, and operations are only performed at one end of the list. Array-based lists are good for bounded stacks, since no reallocation or resizing is performed. In either case, both of them have constant time operations. Our design also made good use of composition and code reuse by using the built-in list implementations. Stack data structures have numerous applications. First, you're probably already familiar with stacks with respect to a program's call stack. As functions call other functions, local state and parameters are stored in a stack frame which is pushed onto a call stack. When a function is done executing, control is returned to the calling function and the stack frame is popped off the top. A stack keeps track of a program's state so that calling functions and methods can be done so efficiently. Of course, a call stack is usually bounded, which is why calling too many functions can result in a stack overflow. More generally, anytime that you want to keep track of breadcrumbs or previous state, a stack is an ideal data structure to do so. Algorithmic strategies such as backtracking or simulating or unfolding recursion can be done with a stack. Many algorithms use stacks as a basic data structure, such as a shunting yard algorithm for parsing mathematical expressions, or graph and tree traversal algorithms like depth-first search and many more. In the next part, we'll explore a related data structure, queues, and explore some variations on both of these restricted access data structures.